the Center for Computational Biology and Bioinformatics, also at Penn State. His main research focus is to use techniques from computer science to analyze biological data and answer fundamental questions in biology. And before joining Penn State, he was a visiting scientist at Oregon Health and Sciences University. And even before that, he was a postdoc at UCSD, and he obtained his PhD from University of Toronto. He is and he has like obtained multiple awards, including the NSF Career Award and Best Paper Award at conferences like Recom. And today he'll be talking about the theoretical analysis of sequencing bioinformatic algorithms. Yeah, without delay, I'll hand it over to Paul. Paul, you can
Okay,
take over.
Yeah, thanks for the introduction. Get this out of the way. Yeah, so I'm not a theoretical computer scientist. I work in computational biology or bioinformatics. But as far as that field goes, I work more on the theoretical sides, and a lot of the techniques that I use are coming from, are the same techniques that basic theoretical computer science use. So there's intersection between the two fields, and there's kind of been a rich history of intersection between the two fields. But there's still, I'd say, a big gap between theory and practice, and what I'll talk about is intended to cover that. So the title of my talk is the theoretical analysis of sequencing bioinformatics algorithm. And the talk is not perhaps a standard talk because it doesn't cover any of my own results. It's covering essentially two survey papers that I wrote that tried to tackle this question, and they did it by looking at the state of the field. So it will be more of like an overview of the field kind of talk than the latest results kind of talk. I should also say that as you can see, the papers were published and actually written now a few years back. So the talk probably is not updated with the latest results that have happened since then. So just keep that in mind. So, okay, when I'm going to talk a lot about theoretical analysis of algorithm performance in this talk. And here, performance, most common measure is runtime. It could be memory use, it could be accuracy. And these are statements like we say insertion sort runs in worst case theta and squared time. This is a theoretical analysis of an insertion algorithm runtime. Or we might say another example, expected lookup time in a hash table is order 1. So the reason why do people do this? So one, there's the field of computational complexity, which is built on this kind of analysis, and that field, I think of it as being more mathematical rather than applied in nature. So the questions that it's pursuing are not really about implementation and application of algorithms, but rather about complexity classes. So here I'm really going to talk about the relationship of this type of analysis, why we do it, to practice, to the implementation and running of algorithms. And here we can formulate this in the goals twofold. And I didn't come up with this. I took it from a talk by Tim Roughgarden, and I don't know how far back this kind of formulation goes, but it's very natural. Those of us that have worked in this field, this makes a lot of sense. So one, when you say that insertion sort runs in worst case theta and squared time, you're trying to predict the empirical performance of an algorithm. Now, whether that kind of analysis actually is predictive of empirical performance is another question. So insertion sort, in this case, it's a worst case analysis. So it could be that on some inputs, the runtime is very different. Now, the prediction is that if you double the input size, the running time quadruples. And we find in practice this is often the case, but for some data sets this is not going to be the case. Right, so that's one of the goals, is to predict the empirical performance. The other goal is to essentially be yardstick for algorithm developers. So you have this n squared algorithm. I'm going to try to beat it, come up with n log n. I'm going to call it merge sort, and now I'm going to run merge sort in practice. And the idea is, because I beat the theoretical runtime, I should also do better in practice. And though there's no though it doesn't have to be that way, in practice we can see something very different. But what has happened is, generally or often, it's been the case that things like merge sort are going to run faster than insertion sort. So in this way, you are by using this way of analysis, you're using it, you're pushing forward the design of algorithms that in the end you're going to want to implement and run on real data. Okay, so these are the two goals I want to keep in mind throughout the talk. And then we get to what are the actual techniques for theoretical theoretical analysis of algorithms. So like I mentioned, the traditional worst case analysis, which we learn and we teach in undergrad classes. So here, the constants, even for higher order terms, are dropped. Right? We don't say theta 2n squared. We look at the inputs as being worst case, not average case, not something else. And the parameter we use to analyze is the input size, not something else. Okay, and then so that's the basic one, and then there are more advanced techniques like parameterized worst case analysis, A of A analysis of algorithms, average case analysis, semi-random models, and I'll talk about these a bit more during the talk. So as a computer scientist, we're born into this field with certain dogmas, so things that are kind of true that we perhaps never really questioned. So here, the dogma, I think, of computer science is that theoretical analysis of algorithms actually does achieve its two goals. So by doing this, we have designed algorithms that work well in practice, and we are generally able to use these formulas to predict empirical performance, right? And undoubtedly, there are several examples where this is true, and this dogma is well earned. But coming from my background, I've been thinking a lot about it with respect to sequencing algorithms, so algorithms that run on sequencing data. I won't really get into the details of that data for this talk. You don't have to really be familiar with it. But general scope is that you have, say, a genome, and you would like to get the string of the genome, but there's no technology that does that. And instead you get kind of a lot of short read samples from the genome, and you get this kind of data with billions of reads, and you do all kinds of things with it. So the motivating question for this work is if theoretical analysis of algorithm has achieved its two goals when applied to sequencing bioinformatics. And right away, I should point out that sequencing bioinformatics relies a lot on black box solutions like integer linear programs or HMMs and so on. That, of course, like algorithms for those have been developed as you could really say that the theoretical analysis of algorithms has led to the development of things like the Viterbi algorithm for HMMs. And so that's definitely true. But sequencing bioinformatics is using these as black boxes. What I'm really after is for algorithms that we are designing specifically for this field, for sequencing bioinformatics, and we're doing theoretical analysis of them. Is it achieving the performance, the design and prediction goals that I mentioned here? Okay, so the plan for the talk, I'm going to try to explore this question both systematically and anecdotally. Systematically, we want to know what are the techniques that have been applied besides the traditional worst case analysis, and to what extent they have achieved the goals. And finally, more constructively, what can be done to improve the situation. So that's a really broad question to ask of a field, and the focus, I gave kind of two ways of digging into this. One is a systematic problem, a systematic approach, a depth approach, where we take one problem, the edit distance, and we dig deep into it to see what has been done. And the other is more an anecdotal approach, which is looking at several areas of sequencing bioinformatics and just getting a gist of what's overall been done and what's the potential there. So I'll start with the edit distance in the first half of the talk, and then talk about the anecdotes in the second half of the talk. So the edit distance problem, many of you have probably seen it, is given two strings A and B of equal length, n, over a constant size alphabet. What is the minimum number of substitutions, insertions, and deletions needed to transform A into B? This is really a unit cost version of edit distance. And it also, just for simplicity of the talk, we're assuming that the strings are of equal length n, though that's not, for the things we discuss for the algorithms, they're usually pretty general, that the strings can be equal length, it can be different lengths, excuse me. But we're not going to consider other extensions here, like weight penalties for these events and so on. Not because they're not important, but just to like make the systematic study narrow enough so that we can tackle it. Now, why edit distance? Edit distance is, I think, in a unique place in that it's achieved a lot of attention in both the theory community and the bioinformatics community. It's been studied in depth in both places. So it's kind of a good place to look at what's been done, because if something nice has been done, it would be here. Let's look
one
first
question.
Yeah.
So in bioinformatics, what is the most important notion of distance? Is it edit distance or other distances like Kendall tau or Ulam distance or like Spearman's foot rule? Those distances are more important. Like, what is the most commonly used measure of distance in bioinformatics?
The most common, I think, is edit distance, but maybe not. But the more general version of edit distance, where you have gap penalties, gap open, gap close penalties.
Okay.
I think that's, people also use the Jacquard distance from Kamers as something that's faster to compute and more lends itself more easily to sketching approaches. Those are the two distances I've seen more often used.
Thanks.
Okay, yeah. Okay, so first, let's see what's the reality of what's used in practice. And basically, I found for this problem, 3 basic algorithms are used in combinations of them. So the first is the Needleman-Wunsch algorithm for edit distance. This is kind of a classic 2-dimensional dynamic programming algorithms that sometimes is even taught in undergraduate. The idea is that we have a matrix of a size n by n, and we fill the matrix going from left to right and going down. The value at each position is the edit distance between a prefix of one string and a prefix of the other string, depending on the position. And we can fill in a cell by looking at the left, the top, and the diagonal values in the cells there. Okay, so we fill in this matrix. There's n squared entries. Each entry takes constant time to fill in, and the answer is going to lie for us in the bottom right corner. And that's the Needleman-Wunsch algorithm. It's not used. It's very easy to implement. It's like 5 lines of code. It's in its own, it's not really used in the fastest implementations, but it forms the basis of other techniques applied on top of it. Okay, so it's at the base of a lot of almost all the implementations. So one of those things that can be done to make this faster is called banded alignment. And the idea is, if the edit distance is small, then the path through this matrix that corresponds to that edit distance will go through close to the diagonal. Right? So the idea is you say, okay, let's pick edit distance some D or whatever band, and we are going to look at fill in this matrix just along this diagonal band. And in the end, we're going to be able to tell, hey, either we found the edit distance that's at most D, in which case that's guaranteed to be correct, or we can tell that we didn't find, we kind of had to go out of bounds, and then we didn't find an edit distance, and then we start again, but by doubling the band. Okay, and in that way, we can sort of be faster. I'll get into more of that in a minute. Finally, there's a bit parallel technique. So this basically asymptotically doesn't change anything in terms of the n squared, but it's just a kind of version of Needleman-Wunsch, which bit packs this matrix in a smart way, and then uses bit vector and like SIMD operations to do this very fast using hardware optimization. So these are kind of the 3 general ideas, and the software that's most popularly used essentially is implementing different combinations of these ideas. There's also specialized hardware approaches, so things that use GPUs or custom processors or FPGAs. I don't get into those here. Just to give you a sense of the runtime, the fastest that I observed edlib, if you take 2 sequences of 100,000 nucleotides, it takes between 1 and 30 seconds to compute the edit distance. So maybe it's not a lot if you have a few sequences to compute, but if you imagine that you have thousands of pairwise comparisons you want to do, then this is going to be very slow. So it's still an important problem to speed up.
What do these percentages indicate? 1 and 50?
I'll get to that in a second, but since you asked, so it's essentially the edit distance as a percentage of the whole length. So divergence of 1% means that there's what, in 100,000 nucleotides, that the edit distance is 1,000. The reason,
sure.
yeah, so the reason why it's faster, if you just think about the banded alignment I described, if the edit distance is small, then right away we'll find it in the first band. The bigger the edit distance, the more time it's going to take, and that's what the divergence there is saying.
Yeah, understood.
Okay. Thank you for the question. Feel free to interrupt. Okay, so that's the practical side of things. I guess I should say before I move on that I'm really here talking about the unit cost at a distance. When you get to more general costs, there are other techniques and tools that have been used. There's other there's other things that I'm not mentioning that are not applicable to the unit cost at a distance, but they would be if I talked about the more general case. All right,
Hi.
so yeah.
Quick question. So in the previous slide, can you just quickly brief over the algorithm? What does gap mean?
Gap?
Yeah, in the Needleman-Wunsch.
Oh, so this, okay, so the match.
Yeah.
Okay, so there's a let me rewind a little bit. There's a correspondence between edit distance and alignment of two strings.
Okay.
Meaning, in an alignment, you say, okay, these positions are gonna be matching.
Mm-hmm.
Now they may have the same character, or they may have a different character, but we say they're matching. And then there insert everything else that's not matching is either insertion or deletion.
Right.
And yeah, so then you can define edit distance as taking an alignment and assigning for a match that has the same character a score of 1, a mismatch, so a match that has a different character is another score, and for a gap, which is a character that's not matched, another score. And you can define edit distance as finding the alignment that optimizes over the score.
Got it.
All right.
Got it. Yeah. Thanks.
All right. Thank you. To time. Okay. Okay. So what has theoretical analysis of algorithms done for this problem when it comes to practice? And I'm going to look at it by separated by types of analyses. So the first is the traditional worst case analysis, and we're going to look at our two questions: the design of new algorithms and the prediction of performance. So this Needleman-Wunsch algorithm, which I presented, is its running time is under this traditional worst case analysis theta of n squared. And I actually looked at the paper, and yeah, I'd say that the authors coming up with it were motivated by getting this running time. So I think we can credit this algorithm that's useful in practice. We can credit traditional worst case analysis with the design of this algorithm. Okay. What about prediction? Does this theta n squared actually predict what happens in practice? So in this case, yes.
One more question is, the algorithm Needleman-Wunsch, was it proposed by Wagner and Fisher, or it was proposed by Needleman and Wunsch? Like, why is it called this algorithm when?
Yeah, so this was a question I had when I was looking through the literature. The Needleman-Wunsch paper introduced the problem and gave an algorithm. It was not a kind of a clean algorithm formulation that, as we would think of it today, and they did not do any runtime analysis. I think they were really interested in kind of data and how it works there. The best I think I could figure out is it's something like cubic if you try to do an analysis of their algorithm. So a later paper by Wagner and Fisher did the theta n squared algorithm. Why is that called the Needleman-Wunsch algorithm? I don't know. I think it's the Needleman-Wunsch algorithm was not introduced by Needleman-Wunsch. Let's put it this way. But that's sort of why that's how it's called in bioinformatics. So I stick with that name.
Yeah.
But okay. I made a point in the slide to say that it's different.
Yeah.
Yeah, so the Needleman-Wunsch algorithm is actually, if you think about it, it's not worst case, it's actually every case. Because we fill in this matrix and we fill in this matrix regardless of the data. We have to do the n squared cells. So it's actually for any input, it's gonna take order of n squared time, theta n squared time. So it's actually very good. The n squared is a very good predictor of empirical performance. So I guess this is good for traditional worst case analysis, but I do want to point out that it's also led us astray. So in terms of being a yardstick by which to design an algorithm, people were looking to improve this n squared, and the fastest known runtime is due to this 4 Russian speed up of Needleman-Wunsch, which is giving you a worst case time of n squared over log squared n. So this is faster in theory. Now, if you look at practice, even for there was a study, experimental study, even for n equal 2 to the 18, you're getting only a factor of 5 speed up. And even for 1 billion characters, you would not exceed a speed up of 10. That's not a lot. If you look at things like the bit parallel techniques or hardware optimizations, they easily give you that kind of speed ups. And they don't have, so the 4 Russians, it takes some care to implement it. So it has not actually been used in practice. Basically, I haven't seen any of the used software implement this. So here kind of the traditional worst case analysis led us astray from a practical point of view. Now, arguably, there's not much more that can be gotten out of this kind of analysis for edit distance. There are barrier results that under the strong exponential time hypothesis, there cannot be a strongly subquadratic algorithm. So, I mean, what you can question the hypothesis, but for people like me or people in bioinformatics, when we see something like this, we kind of lay back and say, okay, well, somebody's going to prove this hypothesis wrong. It's probably going to be from the theory community, not from the bioinformatics community. So as far as we're concerned, we're not going to try to beat this bound. Now, the way this bound is often misunderstood is to say we cannot come up, given Seth, we cannot come up with a strongly subquadratic algorithm, and that's not true. You cannot come up with a strongly subquadratic algorithm under this method of analysis using the traditional worst case analysis as a guide. But if you switch to a different analysis technique, you could very well do a better, like an n log n algorithm. So we go next to theoretical worst case analysis, but not in terms of the input size, but parametrized by something else, some other parameter of the data. And here, one very natural one is the edit distance itself, k. So we want to express the runtime, not just in terms of n, but in terms of k. The banded alignment algorithm, the idea that I described earlier, is kind of a simplified version of a slightly more complicated algorithm. The idea is roughly the same. The runtime there is nk in the worst case. So if I go back here, so we look at a band, and then we double it until we find that we can get the edit distance. So here we're doubling this at most 2k times, and so in the end we're going to have a band that's size k times n. To fill that in, it's going to be nk cells. So this is the runtime we get from banded alignment. Now, the nice thing about it is that there's not big implementation overhead. in terms of data structures or anything like that. It's still kind of a straightforward algorithm. There's no constants hidden behind this nk that would make it impractical. And so as a result, it's used in practice. And in terms of prediction, it does a good job. So one of the things it does is that when k is little o of n, then you get this asymptotic separation from Needleman-Wunsch, and that's really reflected in the fact that banded alignment will run much faster than Needleman-Wunsch in those cases. You also get an algorithm that takes advantage of sequences that have a small edit distance. So Needleman-Wunsch would always go n squared, even if the two sequences are identical. Whereas banded alignment, if the two sequences are identical, it would find it in linear time. So and both in the practical, the implementation would work very fast, and the theoretical analysis gives us that. And then even if in the case that k is on the order of n, so it's some constant d times n, then you don't get any you don't get any asymptotically in terms of n separation. But when you plug this dn here, it does tell you that compared to Needleman-Wunsch, this is going to be faster. So if d is like 10%, then banded alignment will be about 10 times faster than Needleman-Wunsch, and that's something we see in practice as well. So really here, it's a big success, I think, in terms of design and prediction. But again, because of barrier results, there's only so far we can go beyond this, because when k is order n, then you go back to the barrier results I just mentioned. But this k theta n is really important case in practice, and I'll explain why. If you take two genomic sequences between, say, two species, they evolve through some kind of mutation process. And the mutations, roughly speaking, are happening at every position with some probability over time. And that's why we talk about divergence. So there's a divergence, say 1% between two genomes, meaning 1% of the positions are mutated. And that's really the way this kind of distances evolve, is that the number of edits is proportional to the length of the sequence. So this is really a big application of edit distance, and unfortunately in this case we're stuck with the barrier results. There's also you can also do worst case analysis parameterized by something else, not necessarily the edit distance. So there have been attempts using entropy and compressibility of the sequence. And for example, with entropy, if h is the entropy, number between 0 and 1, entropy of the input, then you can get a running time that's h n squared over log n. And similarly, if the size of if you compress the input and you get a size of L, then you have algorithms that are running time about L times n. So unfortunately here...
So what do you mean by compressed input?
Yeah, so if you get, so it depends on the compression scheme. I'm being generic here. So there's a result for run length encoding of a string. The idea is if you take the input, you run some compression like run length encoding on it. That's usually linear time or n log n time or something like that. And you do it for both strings. And now your input is of size L2L, right? And now if you can come up with an algorithm, edit distance algorithm, that doesn't uncompress the strings, but computes it directly on the compressed strings, then you can hope to do better than n squared, because now even if you have like a full matrix, it's L squared. Does that make sense as a general idea?
Yes. So in general, like if you have compressed input which preserves some properties approximately, then is it possible to get some approximation factor? Like we are focusing on edit distance, but instead of computing exactly, in practice, if you get 1 plus epsilon approximation or very nearby approximation, does it satisfy the goal, or you really want the exact values?
I'll go into detail of that in a later slide. Briefly, I think your approximation ratio has to be very small, has to be like 1, close to 1, like 1.1, for example, or something like this, or pitas, something like that. I'll go into more detail.
Yeah. Thanks.
Yeah,
Okay,
and
so
what does entropy of the input mean? Like,
Yeah.
Yeah, can you explain
So-
what entropy means?
Yeah,
here?
so the idea of entropy is like basically the randomness in the input. If I choose a random string, it's gonna have high entropy. If I choose a string that's like a, it's gonna have low entropy. And
Okay.
there's a
And
formula
so-
for entropy, and it's between 0 and 1.
Right. Okay. So like if there is some underlying distribution of the input, then like that distribution will have some entropy, and that is H. That correct?
It's more that it's not it's not with a distribution. It's with an actual
Okay.
input. So you have a string, and you compute the
Whether the
entropy
string
for it.
looks random or not.
Right. Right.
I see. Okay.
Right.
Thanks.
Okay. So unfortunately, this has not really led to anything used in practice. And one of the reasons is that DNA sequences have high entropy and are not very compressible. Right. So this H and L are pretty high. So if H is high, then you really just have n squared algorithm. If L is high, you really just have an n squared algorithm. So yeah, this hasn't led to anything in practice as far as I know. So yeah, the problem with kind of all of these worst case approaches is that they essentially are assuming an adversary, and we're dealing with biological data, and it's not really adversarial. You know, God did not create my genome in a way to make my algorithm harder. It's not completely random either. It has function and so on, but it's not adversarial for my algorithm. So the flip side of that is something called average case analysis, or distributional analysis, or random model. And here you assume that you're drawing the input from some kind of underlying distribution. And then you measure the performance of your algorithm as a function of that distribution. For example, the expected running time, or the running time is n log n with high probability over this distribution, or it's n log n always, but it's correct with high probability over the distribution. So yeah, so this is kind of a popular approach. Now, in terms of analyzing existing algorithms and saying, hey, can we take like Needleman-Wunsch or others and use this kind of analysis to better predict how it performs on real data? The answer is no, because like Needleman-Wunsch is the worst case analysis is every case, right? So you're doing that n squared matrix. It's not going to help you if you're making assumptions about where your input comes from, right? So in terms of performance, we don't have much hope here, but yes, it can lead to the design of new algorithm, right? So we can try to get a strongly subquadratic algorithm in this model. So then the question is, what is the right model? Now, the first thing that comes to mind is not going to work. The first thing that comes to mind is you draw both strings uniformly at random. The problem with that is that one, DNA is not uniformly at random, and two, the two strings A and B, they need to be related. If they're not related, if they're independent of each other, then that's not really the case where you're going to be computing at a distance. You're measuring at a distance because you think that they are related. Okay. So that model is too simple. But one nice result in this field from Ganesh and Sai in 2020 assumes that A is uniformly random, so it still has that assumption. But then it assumes that B is the result of mutating A with some substitution, deletion, and insertion process with some constant probabilities of those events. And they give an algorithm that is runs in n log n time and is with high probability on this distribution correct. So n log n would be really nice. Now, unfortunately, the algorithm hasn't been implemented or tested. And so it's really an open question of whether when you run this on real data where these assumptions are not met, what's going to happen, right? So it could be that you're still essentially getting this running time unless you really do something crazy, and you're still getting the right input even if you're doing something not according to the process. Or it could be that once you're doing things different from this process, all hell breaks loose and then nothing works. So you don't really know until you try, and this algorithm hasn't been implemented. There's been another, after I wrote the surveys, there's been another breakthrough paper that does get further along here by analyzing under a similar model an existing algorithm that's already been implemented. And there, that hasn't led to the design of a new algorithm, but that has been a way to predict the performance of an existing algorithm. Okay, then the problem with the average case is it's like the other extreme. Now you don't have any adversary at all. Okay. So somewhere in between, some kind of compromise between worst case and adversarial is the semi-random model. Here, the input involves some kind of adversarial choices and then some kind of randomness that's added following a distribution. Smoothed analysis, if you've heard of it, is a classical example here. And then when we measure the performance of an algorithm, we do it with the worst case over the choice of the adversary and average case over the random distribution. Now, in our case, we need some kind of middle ground. So as I mentioned, A should make some kind of sense biologically. It's not just a random string. And A and B must be dependent on each other because that's how the mutations work. So smooth analysis, for example, has been applied here under some version of this semi-random model. Here, the adversary chooses a longest common subsequences positionally of A and B. So it fixes which positions of A and B are going to be sort of matched, going back to the alignment idea. And then you perturb, you add random noise everywhere, but you make sure that when you add to the shared positions between A and B that it's the same. So if you mutate something in A, you also mutate it in B. So you do this identical perturbation in the shared sequences. So this kind of captures some aspects of how these sequences come about in practice. Now, unfortunately, I think in this paper there was it was an approximation algorithm. The approximation ratio was not stated in big O notation. So we don't really know what constant it is or could be. And there have been a lot of follow-up work coming up with approximation algorithms here. So I think at the time I was writing this, the best I could find was a 1 plus O of little o of 1 approximation ratio. Now I should say that, let's say you're trying to tell the difference if the sequences diverged by 10% or 12%. Well, you can't have an approximation ratio of 2 because then you won't be able to tell those apart. So you really need something where it's just close to 1, and this paper achieves that. But the expected runtime it's strongly subquadratic, yes, but from a practical point of view, 1.898, in order for that to actually beat n, it's not beating n squared by a lot. So even for a large n, this is less than a 9 times speed up. And as we mentioned, that really doesn't justify the complexity of trying to implement this algorithm. So, and there's other results here. It's really a promising active direction, but it hasn't achieved the design goal so far. And in order to do that, I think the approximation ratio has to be small, kept at this level, but the runtime needs to really be something much smaller. And then it has to be something that's easier to implement. Okay, another idea, it's a little bit outside of the box, is the following. They say, look, the edit distance, when you formulated your problem as edit distance, it was some kind of approximation of what you really want to know, right? You formulated this problem so you can solve it, but if you go back, you could maybe pull out some other information that's useful. And you can feed that in, that kind of advice into the algorithm. And that's been applied here. There's the idea that, well, if you have an input A and B, and let's say you also have access to log n correlated instances, then there's an algorithm that can find the edit distance in n log n time with high probability. So this would be great, of course, but correlated instances in this case, it's not clear how you would really get that in practice. The correlated instances are pairs where the positions that are matched and edited, those sequence of positions are correlated to the ones in A and B. And yeah, so I don't know if that's the kind of thing we could get in reality. Okay, so maybe I guess the question is how much time I have.
10 to 15 minutes.
10 to 15 minutes?
Yes.
Okay. Okay, so let me, that was kind of a systematic look. And I think for edit distance, we did see the design, the theoretical analysis of algorithm have an impact in practice, but it's been a while. So those algorithms were in the 80s, banded alignment, for example. And so the more recent stuff really hasn't been, hasn't really achieved design or prediction goals. Except perhaps the one paper that I mentioned for using an analysis. I didn't talk about it, but of the seed and extend algorithm. Now, now I want to kind of go more anecdotally and cover a couple of areas within sequencing bioinformatics and see if how theoretical analysis has impacted the field there. So first, kind of the success story, and these are the success stories coming from compact or succinct data structures. If you know things like the Burroughs-Wheeler transform or FM index, this is an example of those. So the idea here is that you look at the bits that a data structure takes, but you're keeping your higher order constants. So there's a difference between 4n bits and 3n bits. And you're trying to come up with algorithms to improve on those constants if possible. So yeah, this has really been successfully applied and developed in sequencing bioinformatics. There's here lots of examples. One is Bosch data structure. It takes 4m plus little o of m bits number of edges, and it's used as a basis for tools that are really widely used in practice. And that's sort of the oldest, I think, example that I could find. There's a lot more. So this is kind of a success story. A not so success story is the field of genome assembly. So I mentioned that you have this long genome, think like 1 billion characters, and you want to get the sequence, but technologically you can't pull out the whole sequence. Instead, you pull out kind of short, think like a couple hundred characters, short samples from the sequence. They're just uniformly random samples, and you get like a lot of them. You get many billions. So every position you expect many of the reads, many of the samples to cover it. And the idea is now from this data, can you reconstruct the whole genome sequence? And there's really not been much in terms of theoretical analysis of accuracy. And I'm talking about accuracy because here that's probably the most important aspect. There have been a couple approaches that are worth mentioning. One, the idea is to measure what percentage of inferable parts of the genome, what percentage of the genome can be inferred. That's kind of technically challenging and hasn't led to, hasn't been implemented in a practical assembler. Another line of work is to measure under which conditions an algorithm can fully reconstruct the genome. So if your reads are long enough and you have enough of them, then you can get reconstruction of the genome that's accurate. This kind of idea has led to an assembler, but it's not really something that's been widely used. In practice, most of the algorithms that we see, their design is driven by just running it on real data. And they rely on complex heuristics that even if you wanted to are would be pretty difficult to analyze. So here we really, really there's not been much of a success in the design goal and neither in the performance goal. So what's the problem? The field is thriving. There's a lot of genome assemblers. What's the limitation of not having had theoretical analysis make an impact here? Well, there was a comparison between different assemblers to measure their performance. And what they found was that depending on how you choose your experiments for evaluation and which data set you use and which metrics, the rank of the assemblers can vary a lot. And one reviewer kind of summarized by saying, on any reasonable challenging genome and with a reasonable amount of sequencing, assemblers neither perform all that well, nor do they perform consistently. So, yeah, so just to summarize here, these are exactly the type of problems that theoretical analysis was designed to alleviate. To alleviate this dependence on which data set you run on, which compute, how you evaluate. If you rely only on this, of course, this is an important way of doing it, but if you rely only on this, you create problems. And we've seen that in this genome assembly field a lot. So what's helped it out in practice is that the technology has improved and the read length has improved. And so you've gotten improved genomes that's been driven more by the technological advances in the sequencings rather than in algorithms. So, okay, it's time for me to wrap up. There's more of the outlook. So going back, if you look at theoretical analysis, has it met its goals of design and prediction in sequencing bioinformatics? Is that dogma justified in this case? And so anecdotally, from my experience, most papers do not perform theoretical analysis, or if they do, they will perform it. They'll say, yes, this is n squared time, but in practice, the algorithm works much better. So it's in that case really not capturing why an algorithm performs well. And the impact has been limited. The impact of theoretical analysis has been limited. There's many reasons for this. So I highlight some here. So, the thing is, we all learn traditional worst case analysis, how to do that. We learn that in undergrad, maybe grad school, but it's really too pessimistic for real data. And that's our comfort of what we can apply, but it's not good enough. Now there are fancier techniques, the semi-random models and so on, but then you really get into the question of, well, if you're working in bioinformatics, your expertise is really in not in theoretical computer science usually. So there's not many people that can do smooth analysis that is working in bioinformatics, right? So there's a question of background of researchers. And finally, the field itself evolves very quickly. The technology evolves very quickly. So you can't take months to work out an analysis of your algorithm and then to go back, to change it, to apply it. It really has to happen quickly. And as soon as you get something that works, you tend to be happy. There's some exceptions like edit distance or assembly. These are problems that are fundamental enough that people have had time to invest more deeply in it. But then a lot of other problems, you don't have that luxury. So that begs the question, is it even necessary to do theoretical analysis? And I think I touched on this. Of course, empirical evaluation is important, but it's not enough. And we saw this in genome assembly. It would be great if we could have benchmarks and critical assessments of algorithms that could also be a great yardstick, but these are not always available. And even when they are, you might have incentives to overfit the benchmark. And then we're stuck with the idea that the performance of the algorithm doesn't generalize well. If you ran it in your paper, you evaluated it on some data set and it worked well. It's quite often the case that in somebody else's hands and some other data, it won't work well. So I do think that it's necessary, and we should try to make some progress in making the theoretical analysis kind of more applicable. So with that, I think we should think of this as its own goal. Can we even look at previous algorithms that we already designed? We know they work well in practice, but can we come up with techniques of analysis that can predict that performance? So even if that maybe in the short term doesn't lead us to some new information, new biology or new algorithm, it's very useful to figure out which techniques work. So and in general, the issue here is that in order to do this kind of thing well, you either need someone who's really talented and understands both theoretical computer science and biology well, or more commonly, you need a team of like matched expertise that can work well on this. So I think I'll stop here and take any questions.
Okay. Thanks, Paul, for the nice talk. Does anyone have any questions?
Yeah, I have a couple of questions. So one is, what other problems are, apart from edit distance, in string algorithms, like what other classical questions are important in bioinformatics? For example, longest common substring or those kind of problems. Like what other kind of classical string questions are important?
Well, so I think edit distance and that whole family. So LCS is kind of a version of edit distance. I think of it, and then more general. So that family is very important. Then I think data structures for querying membership becomes very important. So the FM index, and then it's not really like a clean algorithm problem, but it's saying, can we represent the data in as much as some little space so we can answer certain kind of queries? So I think those are the big question, to build databases from existing sequences.
So I mean, I understand time is one resource, but space, I mean, other paradigms of algorithms like streaming algorithms or online, are those also important in this context?
Right. So one thing that's kind of so memory is a big bottleneck in a lot of these algorithms. So they're that brings in streaming. A lot of times you have an algorithm that becomes really bottlenecked by the I/O, and in that case, it's not strictly a streaming model in the sense, well, you can do multiple passes over the data. It's there usually, but you'd rather not, or you'd rather limit the number of passes. So that, I think algorithms for the streaming community have found a home also in applications here. Yeah, I mean, in terms of online, yeah, not so much that I can think of at the top of my head. Yeah.
Yeah, basically, I'm interested in a list of questions which are important to the bioinformatics community, but it's a clean theory question. And the classical ones are hard, of course, but among the new paradigms, if there are some other interesting questions, like in the distributed setting or dynamic setting, if some questions are not well studied, and they are actually probably needed from the bioinformatics community, that they needs to be studied.
Yeah, that's a common question I get from theory folks. It's actually quite rare to have like such a clean problem. It's kind of misleading because you'll read a paper and you'll say, well, here's the problem formulation, here's why it's important, here we solved it, and a theory person reading and says, well, we could have done this, right? But usually what's behind the scenes in these kind of things is an iterative process where, let's say I'm working with a theory person and I say, well, I'd like to solve this question I have. Here, I formulated a theoretical question, can you solve it? And you tell me, of course, I cannot solve it. This is too much, blah, blah. Here, I have a simplified version. Does that work for you? And I tell you, no, this is like not going to work well in practice. And so we iterate like this until we get to some problem formulation where you say, hey, I think I can solve this. And I say, hey, I think it might work if you do solve it in practice. All of that doesn't make it into the paper, right? So it's just not in the formulation. That's the more kind of common way to get at these kind of clean, in the end, what are clean problems.
Another question is, like, in practice, are people using a lot of deep learning or ML techniques nowadays in solving these problems, or it's too hard for ML methods to handle?
Yeah, I haven't seen ML methods for at a distance. For other algorithms for data structure, there's some work, but I'd say it hasn't been disruptive yet in a positive sense.
Thanks. These are my questions.
Thank you.
Any further questions? Okay, if not, let's thank Paul for the nice talk.
Thanks a lot.
You.
Yeah, and we can.
Thank you for having me.
Yeah, I'll stop the recording.